All right, so in the real world, it's never quite ideal. Sometimes you can't find two experiments where all of the substances are constant. In that type of situation, you have to use an algebraic method, and remember to do that last. Okay, we're going to do an example, and although it's not absolutely necessary in this case, our example, we're going to do that in part D. Okay, so example 2, which is this one here, part D, we're going to demonstrate this method. The reaction below is between bromate ions and bromide ions and hydrogen ions. The table below gives us the results of 4 experiments. And we're going to be using this to answer the following questions. Determine the order of the reaction with respect to bromate. Justify your answer. Determine the order of the reaction with respect to bromide and justify your answer. Determine the reaction with respect to hydrogen ions. Justify your answer. Write the rate law of this reaction. What is the overall order of this reaction? And determine the rate constant for the reaction, including units. Finally, calculate the rate for experiment 5. This is challenging for a few reasons. One thing, it's the first time that we've had 3 different reactants, and we want to find the order of each. Start with bromate. We want to pick something where bromate is the only one that's changing. I'm going to go with experiments 1 and 2. I see that bromate is doubling, but the others are staying the same. So what we want to do is look at the rate. Okay, bromate is doubled. The rate was also doubled. You want to be able to do this kind of thing in your head. You see that we've got 8.0 times 10 to the negative 4th and 1.6 times 10 to the negative 3rd. 10 to the negative 3rd, that's a little bit of a bigger number. Okay, so I could write this as 16 times 10 to the negative 4th. It's just another way of writing the same thing. 16 times 10 to the negative 4th. Then you can easily see that 8 is half of 16. So we know that rate and the bromate ions are directly proportional since they're changing by the same factor. Concentration of bromate is first order. The rate is first order with relation to bromate. Now we want to determine the order of the reaction with respect to bromide, Br minus, and justify the answer. Alright, so I want to pick something again where everything except for bromide is the same. I'm going to go with reactions, experiments 2 and 3. Again, the rate is, I'm going to do the mathematical method on this one instead of just working out with words. You could do that the same way we did up here, but we're just going to use the algebraic method. So remember, our rate constant is K times the concentration of bromate to the N power times the concentration of bromide to the M power times the concentration of H plus to the X power, just 3 different exponents. We don't know what they are. All right, so we want to compare experiments 2 and 3. Experiment 2 is on top. The rate is 1.6 times 10 to the negative 3. The rate of experiment 3 is 3.2 times 10 to the negative 3rd. We got that from right here. And then we're going to plug in the values. The concentration of bromate in 2 is 0.2. In reaction 3 in experiment 3, it's also 0.2. That's to the N power. And now we have bromide 0.10 in experiment 2. And in experiment 3, it's 0.20. Then finally, H plus is 0.10 in both experiments 2 and 3. Let's look at what we can cancel out. Well, 0.20 to the N and 0.20 to the N can be canceled out because they're identical. K and K can be canceled out. 0.10 to the X and 0.10 to the X can be canceled out. But 0.10 to the M and 0.20 to the M, we can't cancel that out because we don't know what M is. But we can divide those and raise the answer to the M power. And of course we'll divide this. We end up with 0.50 equals 0.50 to the M power. Well, the only number that M could be to make this statement true is 1. So M equals 1. The reaction is first order for bromide. And part C. We want to determine the order of the reaction with respect to H+ and justify our answer. Now, there's more than one way to do this, but we're going to solve this with a mathematical solution using experiments 3 and 4. I'm intentionally using 3 and 4, even though there are other choices that I could use, because everything's changing. The reason I did that is because from part A, I know that N equals 1. From part B, I know that M equals 1. And I wanted to illustrate that if you can get that far where you know the order of two other reactants, we can find this order even if everything's changing. So I'm just going to plug that all into the rate expression. We know that bromate is first order and bromide is first order. We just need to find the order of H+. Those are going to cancel out. And the rate is the same in those two, which was kind of interesting, right? K and K will cancel out. And then we will do our division with everything else. You end up with 1 equals 2 times 2 times 1/2 to the X power. So I'm going to do 1 divided by 4, 1/4 equals 1/2 to the X power, which means that X has to be 2 in order for this to be true, because 1/2 squared is 1/4. The reaction is second order for H+. Now we want to write down the rate law for the reaction. The rate would be K times the concentration of bromate times the concentration of bromide times the concentration of H+ squared. What is the overall order for this reaction? Well, I've got first order, and second order. I've got to add those up, 1, 1, and 2. I end up with an overall order of 4. And then part F, determining the rate constant for the reaction, including the unit. First, our rate equals K times BrO3 minus times Br minus times H+ squared. And we know we can rearrange that so that we can solve for K. K equals the rate divided by those factors there. We're going to use experiment 1. My rate is 8.0 times 10 to the -4th, and I've got my units written here. 0.10 moles per liter, or moles times inverse liters. 0.10 moles times inverse liters, and then 0.10 moles times inverse liters, and I'm going to square that one. So let's pay attention to our math as we go. I've got 0.1 times 0.1, that's 0.01. 0.1 squared is 0.01, so I'm going to do 0.01 times 0.01, which is another way of saying all of that is 0.1 to the 4th power. And then I've got 8.0 times 10 to the -4th on top. Okay, moles times inverse liters times inverse hours, and then down on the bottom, we've got to raise our units also to the fourth power. So moles to the fourth, liters to the negative fourth. I end up with 8.0 moles to the negative third, liters to the third, inverse hours. And to calculate the rate for experiment 5, we're just going to be plugging it in. We're going to plug in all this information into the rate law we just figured out. 8.0 times moles, inverse moles cubed, liters cubed, inverse hours, times 0.30 moles, inverse liters, times 0.30 moles, inverse liters, times 0.30 moles inverse liters squared. And the rate we come up with is 0.0648 moles, and let's do those units. Moles to the negative 3 plus 4, it's going to be to the first power. Liters to the 3 minus 4, that's going to be negative 1, and then inverse hours.